Hello, this is Bill Spangler with Zwick Valve, National Sales Manager, or actually International Sales Manager with Canada included. I'm here today to give you some information about the Zwick Valve, how it works and where to use it and things like that. So let's get started. This is a triple offset valve. It's metal seated. It's tested to zero leakage in low pressure air and high pressure water, so it definitely has a shut-off capability beyond what the normal valves are that the customers use. The 3 offset design allows us to operate without rubbing. 2 pieces of metal come in contact only at one point, and that's the closure point. The valve was designed and developed to replace gate valves in steam, and the steam applications are about 35% of what we sell. It's been adopted and adapted into the refinery and chemical industry and all kinds of other types of industries where steam is involved, or chemicals that are compatible with the metallurgy that we can provide, or let's say other alternative applications that are usually not considered important enough to use an expensive valve, but that if it does leak, it causes a big problem for them. So let's get started with the gate valve comparison. Again, it was designed to replace gate valves. There are 5 things wrong with gate valves, actually 6 if you count automation. Number 1 problem with gate valves is that they leak virtually from the get-go. They're not tested to make sure they don't leak, so you can buy a brand new gate valve and it leaks. Number 2 is operability. If you turn a gate valve, you know that it's a lot of work, and the operators love having a quarter turn type valve because it takes a lot less effort to turn and to seal. The third thing is stem packing leakage. You virtually eliminate stem packing leakage due to the fact that it only moves a slight amount, a quarter turn, versus a rising stem gate valve that travels up and down through the packing, which causes a lot of problems with packing leakage. That's number 3. Number 4 is size, and number 5 is weight. There are some issues, especially when you're in a tunnel or a hallway or a manhole, with size of valve. We can actually take a gate valve that's, say, 12 inches tall or 12 inches in diameter, and it's a very tall valve. We shrink it down to basically the line size. So you have a much more space in this manhole or tunnel or wherever you're putting the valve that has limited space. The 6th thing is automation capability. Of course, with a quarter turn valve, you can use a pneumatic quarter turn operator. You can use an electric operator. You can use an electro-hydraulic operator. So there are lots of options when you use a quarter turn valve. Now, as far as the valve is concerned, we call it a triple offset valve. It's actually, I call it a hybrid valve. It's a mixture between a gate valve and a butterfly valve. It has what you like about butterfly valves in that it has a quarter turn small package, as we spoke of before, and we eliminate the soft seat and we eliminate the rubbing that happens in a quarter turn butterfly valve. On the hybrid gate valve side of this design, we have removed the gate valve linear motion up and down. We have also removed the rubbing that the gate valve has when it seats the gate down into the seat. So what you end up having is the best of both worlds. You have an all metal seated valve that is zero leakage and doesn't rub and doesn't have interference fit type seating as a butterfly valve does. So going from that point, we call this a triple offset valve. So we would want to know how to explain what the triple offset is. So if we can look at this diagram, if we start with the standard original butterfly valve design, you can see that the shaft is centered in the middle of the body and in the middle of the pipeline and in the middle of the disc. So you're completely centered, no offset. So this is a zero offset valve. The design or theory of shutoff of this type of valve is that the disc is actually bigger than the inside diameter of the seat. So as you close this valve, it displaces the rubber by the amount of the oversize of the disc compared to the seat. To do this, to achieve this, you have a lot of rubbing and a lot of wear. The rubber compensates for that, but of course rubber has limited features on it. It can't take very much temperature, and of course pressure will just rip the rubber right out of the body, so it would be limited in pressure and temperature. This valve was used mainly for water service and oil field trucks that would go out and collect ambient temperature oil or ambient temperature water or some temperature water up to what the rubber seat can take. After using this in those applications, people understood the benefits of this design over a gate valve, and they clamored for better butterfly valves that can go into more applications. So when the material Teflon was developed, they ended up putting a valve of this type, centered design, with a Teflon seat, which still had a lot of rubbing, but it also had issues with pressure, and now you had an elevated temperature, but not all the way up to metal, and you had more applications you could use it in, but not as much as metal. So the Teflon seated centered butterfly valve, which is still in use a lot today in certain chemical plants, was the first version of a Teflon seated valve. Then they recognized that if they could take a strip of the Teflon or a ring of the Teflon, install it, as you see in this picture, as a ring with a retaining ring to clamp it in place, they could elevate the pressure and the temperature above the original design. The problem in the new design was that it had one thin ring of contact all the way around, and having the shaft in the middle of the disc, as in the first version, was going to be a problem, so they had to move it back. When they moved it back, they achieved 300 total operation without the shaft being in the way. And what they found was that from about 30 from the open position to 30% closed, there was no contact with the seat. A smart engineer decided that if he could take that shaft and not just move it back but over to one side, he could reduce that rubbing down to close to the seat, about 10% open without rubbing. And that's exactly what the high performance butterfly valves of today with the double offset, that's what they achieve. They achieve about 90% of travel without rubbing, 10% of travel, the last 10% being where they rub. And in this 10% of travel, they're crushing the seat outwards, because in this design also you have a disc that's bigger than the seat you're putting it into. So as it comes into the seat, it rubs and squeezes the Teflon outwards. Now, this is a design that's still used today, and it's very popular in a lot of applications that are not too critical, not too high temperature, and not too much pressure, because it's not a fully rated valve. The next step was to go to a fully rated valve, all metal, and in order to do that, what they wanted to do was to eliminate the last 10% of travel that I mentioned that this design rubs. And the way they do that is they measure the angle of the disc at the point of contact versus the point of closure. And when they machine the seat and the seal ring, instead of machining them on a straight line down the pipe and down the valve, they measure this angle of contact and they adjust the machining angle of the cone over to that angle, and you end up with a tilted cone, as you see in this picture here. What that achieves is you move the contact point by tilting the cone to be right in the closure point. So now you've achieved contact and closure at the very same point, which is what they needed to achieve in the first place. So this is what's called the third offset, and it achieves, for every valve that has it, a total closing from the 0 point to the 90-degree point without rubbing. Okay, well, having explained the three offsets to you, now I'm going to show you the cutaway of this valve, the demo cutaway. It has an open position here. As you can see, as I turn this to the closed position, there's no interference fit during travel, 90 degrees from open to the closed valve. When it hit, you hear that, it has hit the seat and it has stopped. The seat is the stop in this valve, so we never want to have an actuator or a gearbox that has a stop that keeps it from hitting that seat. If it does, it will leak. Also, it has to be set for over travel, so it can't be set just for 90. It has to be set for 91 or 92 degrees, maybe even 93, to allow for the torquing of the stem to energize or put force on this ring against this seat. So the way this valve works is, as we close the valve, it hits the seat, it stops here, it cannot go further, and the reason why it can't is the seating cone that we discussed earlier, it has a bevel to it that's so wide, and the bevel on the seat that matches the bevel around the seal ring, when it hits that seat, it will stop and it will allow for more travel only at the top of the valve, at the top of the stem. It will stop here. So what's going to happen is the stem, which is one full stem all the way from the bottom to the top, will move a degree, maybe 2 or 3 at the top where it stays stationary here, but it is feeling the load, the torque, the torsion of the ring pushing against that seat, which is what achieves our shutoff. If you remember, the previous valves we talked about had this interference fit where the disc is bigger than the seat that you're putting it into. So when you take away the interference fit, you can eliminate not only the rubbing that the three offsets eliminate during travel, but you can also eliminate rubbing when it hits the seat. So there's no interference fit that you have to adjust or compress something into something else. A disc into a seat, for example, or a gate into a seat. So by achieving these two designs, from the triple offset to the cone and cone 25 degree cone and cone design, you have completely eliminated wear on the valve. Now by designing this triple offset with the cone and cone with the 25 degree bevel, or 25 degree cone with the it actually is 12.5 degree bevel on each side of the cone, which adds up to 25. What we end up with is, when we seat, we only hit the seat at one point. Our major competitors have a different design. They have what they call a flexing ring. We have a static ring. The flexing ring design is shown in these pictures on the screen here, where in the open position you can see a large, or a fairly large, white area right here. That is a space located behind the ring and between it and the hub of the disc. And what happens on this design is, when this ring contacts the seat, it is pushed down this taper, because their taper is less than 12.5, or it's a less than 25 degree cone. By design, they need to do that in order to push this ring inwards, and at the same time it moves in this direction towards the inside of the diameter of the inside hub of the disc. It will move inwards like this, and when you actually seat it, you can see the space that was here in the open position is now gone. And the reason why is, again, because you've pushed this ring down this taper. It has become smaller all the way around. It's become a little bit less in diameter, which means that this ring is now in compression. And that's how the force for the seal on this valve is achieved, through compressing this ring. Remembering that in our design, there is no force being applied to the ring which would cause it to compress, because it has a 25 degree angle. It cannot move forward, so when it hits the seat, all the force you put on the stem is manifests itself by the ring being pushed against the seat tighter and tighter. So our shutoff is achieved through torquing of the stem, and it's stored in the top of the stem area, whereas in the previous design, or the original design of the flexing ring design, it is stored in the ring itself, and the stem is turned all the way to 91 or 92 or 93 degrees, and the ring is storing the force in there. Three problems with this design. Number one, you have more wear because you hit and you move. We hit and stop, they hit and move. So when they hit and move, you're causing wear on the seat. Therefore, they have a stellite seat requirement on their valve because of the wear, just like a gate valve does. The second thing is, once it's in the seat, it's stuck, and when you go to open the valve, it has to be torqued open, so to speak. There's a torque requirement to open the valve that's higher than to seat the valve. So when it does open, it will jump off of the seat. In some cases, that's not a problem. In some cases, it is a problem. So we need to know about that if we're going to be competing against this valve. The third thing is that we have a gasket behind the ring, between the ring and the disc. We have a soft graphitic gasket similar to what you would see on the head gasket of a motor engine. The bolts on the front of the disc will compress that and seal the leak path around the ring and out the other side. If you seal around the ring in the valve seat and between the valve seat and the valve seal ring, you don't want to have a leak occurring behind the seal ring, which defeats your whole design. So you have to have a gasketed seal here. They also have to have that leak path sealed, but they cannot use a graphitic gasket like we do, because the movement of the ring back and forth will fail that gasket shortly after being used several times. So with their design, they machine a groove behind the ring, and they drop in a flexitalic gasket, but it's still a gasket and it still sees that movement. And if you have something that's cycling fairly often, it will fail in a very short period of time, comparatively. So this is a failure point. These three issues do not exist in the Zwick valve. One other design difference between us and the other valves of this type that are out there, triple offsets, is that we have a non-pinned disc. And the reason we have a non-pinned disc is we understand that, as in this design, when you have a pin locking the disc to the shaft and then a keyway to provide torque for the seating, the pin is there for locating the disc relative to the seat, which has to be adjusted at the time of manufacture and assembly for the valve to actually be lined up between the ring and the seat properly, so that you don't wear the valve unduly because it's not lined up. So there's adjustments built into the bottom of the valve that will raise and lower that stem a little bit at a time, and allows them to align the disc with the seat. This is all done in an assembly area, which is at ambient temperature. They ship this valve off after assembly to the testing department and test it, and now our customers get this valve out there in the field. They apply it to a steam line that has 300, 400, 500 degrees on it, and what's going to happen is there's going to be thermal changes in the metallurgy of the valve. So the valve that is carbon steel in the body with a stainless steel type shaft of some type, 400 series, or whatever shaft material is different than the body, so it will grow at different rates. So what happens is the shaft will grow at a different rate than the body, and the alignment that you had with the ring and the disc aligning with the seat is no longer valid. So you should be able to go back and readjust that, but you cannot do that while the valve's in service. So you are actually stuck with what you get. With our design, we extend the bearings inwards, and we allow for 2 keys to torque the valve, but it's not actually attached to the stem with a pin. And the way we limit the travel is, again, with the bearings being extended inwards towards the disc, we allow just maybe a 32nd of an inch adjustment up and down to readjust automatically or self-adjust to a new set of temperatures. And over here at the valve, you can see the space right here, and we have adjustability of, like I said, about a 32nd of an inch up and down, which allows it to readjust. Now this is exaggerated for demonstration purposes, but that gap right there is always there, and it is there to adjust or to help the valve self-adjust to a new set of temperatures. One thing that the Zwick has that no one else has, as far as availability of a unique feature, is the special sealed bearing that we have that is an option in the Zwick offering. So what is the sealed bearing? It is a bearing that has a packing built into it. In the inside, we have a housing. The actual bearing rests on top of that. This is the follower. The inside diameter rests on top of that bearing, and when you tighten the bolts here and the bolts on the bottom, it crushes that seal inside here, which seals the fluid in the pipe from getting up into the bearing. This is a great product for anything that's polymerizing, or for sulfur, tail gas, or molten sulfur, things like that. Very dirty surfaces where you're worried about trash and garbage getting into the bearing itself and causing the valve to seize up. If you have these bearings in there, you won't seize up your valve. The other thing is that we can talk about is emergency shutdown valves. Any emergency shutdown valve is required to move when it's needed, and that could be 8, 5, 10, 15 years down the road, and having these bearings installed in your emergency shutdown valve, which should be a Zwick, to have this would be a big advantage, because the bearings would be clean for whatever time that they're in service. So you could always depend on the valve to move. Actually, you could actually make a case for any actuated valve to have sealed bearings, just because if over time your bearings get fouled up, and over time the seals on the pneumatic actuators that you might be using would lose some seal, and you'd lose some force. There may be a time when the amount of force available is not equal to the amount of force required, and the valve won't move. So I believe that the sealed bearing, which has another set of packing at the top which seals the outer leak path, at the inner leak path, when these are installed, you can depend on the valve to move even in dirty service. So we recommend seal bearings for those types of applications. The demonstration valves that you'll have, the demonstration valve has a sealed bearing in the top to show them what that looks like, and in the bottom of the valve you'll have our standard bearing, which is for pretty mundane services like steam or let's say any kind of hydrocarbon in a manual isolation type application. This is all going to fill up with fluid, but if it's not something that's going to foul up, it shouldn't be a problem. Another available option with the Zwick valve is a double block and bleed valve. This is a very handy device to be offering to especially refineries and some steam plants where they're needing double block and bleed for safety reasons, because in the past, if they wanted a double block, what they would have to do is add another valve by cutting pipe and welding a spool piece together and welding a flange on the downstream pipe, and then buying another valve and installing it there. With the double block and bleed Zwick, which has two valves and one gate valve length body, you can remove the gate valve that's presently in there, slide the Zwick double block and bleed in, and that would be the end of it. You would be done. No welding, no cutting, anything of that nature. The Zwick valve is also offered as a check valve. It's a little bit modified from the normal Zwick valve, but we move the shaft slightly over to the side more and then turn it on its side, and it becomes a tilted disc check valve design. So we have a weighted arm here and a hydraulic dampener to allow the valve to not slam closed like a normal check valve would do. It would not slam the seat. It would be a buffer or a damper for the last bit of travel. We can also extend the shaft out on the far side and apply an operator to this valve, and it now becomes a stop check valve. And when you have a stop check valve, you can eliminate a block valve, because now your check valve doubles duty as a block valve. And the way it works is there's a declutching mechanism on the shaft on this side that would only engage when force was put on that end of the shaft. It would turn it and it would engage, and now you can operate it as a block valve. manually or electric operator or pneumatic operator. So that's a nice feature to have, but it's not any good for gas type services, steam. It has to be a fluid or a liquid like water or some type of fluid. Zwick has also partnered with a company called Sharktooth, and that company manufactures a ring that has a set of slots. They call them shark teeth, or the shark tooth, and it applies to the downstream side of our A1 butterfly valve body, and as the valve opens, it gives you control from the 0 to 20% open that butterfly valves traditionally have trouble with controlling in that area. Once you reach 20% open, then the shark tooth stops and the disc begins to do the work, and the disc itself can control very well between 20 and completely open. We have the pictures here of the closed, partially open, and all the way open. And we also can show you here what the shark tooth looks like, and this is the assembly. You have a gasket here. It fits between the shark tooth raise face and the raise face of the valve. You bolt it up to the valve, and then you pinch. The bolts are only 2 or 3, depending on the size, maybe 4 of these bolts that hold it in place. So you have to buy, between the 2 flanges, you have a wafer type setup where it crushes the shark tooth ring against the gasket between that and the valve and seals there. You have a gasket on this side and a gasket on this side. So now you've got your control valve installed, and it works similar to a V-ball. As you know, the V-balls have a slotted V that allows you to control from the low end to where the valve is completely open. This does exactly that for a butterfly valve at about 2/3 the cost. So this has been a quick overview of the Zwick and the design of the triple offset and how the Zwick works, and also the features and benefits that are offered by Zwick. If you have any questions, please feel free to call me. My number is 713-444-0521. I'm usually on the road, but I'll answer you as soon as I can.